we learned that there are three principles in designing experiment. First one is replication, second one is randomization, third one is local control of error. According to way these principles are applied in designing experiment, we can divide our experimental designs into three. Those are completely randomized design, stand by CRD. Second one is randomized complete block design, denoted by RCBD. Third one is Latin square design, denoted by LSD. So we have three conventional experimental design. First one is completely randomized design. Here, this is the most simplest type of experimental design that we have. This experiment design we can use only in homogeneous situation. That means if we can find homogeneous land area, or if we can find homogeneous experimental material, and we can provide same condition to all the experimental unit, then only we can use CRD design. We know we can provide same condition in the laboratory setting. Therefore, CRD can be used for laboratory experiment, lab experiment, because we can control temperature, light, RH. We can provide same thing to all the experimental unit. In greenhouse, also we can control environment and provide same condition to all experimental unit. Also, in the field, we can find small land area which is homogeneous. Homogeneous same moisture condition in this land area, and same soil condition, same shade. Likewise, small area we can find. But when the area is getting large, we cannot provide homogeneous condition. Therefore, we can use CRD design for small field experiment, not large experiment, because in the large, when the experiment is getting large, we cannot find homogeneous land area. Using in large field experimentation are limited due to impossibility of finding large homogeneous land area. Here, randomization is done to all the experimental unit at same time. Assume we have three treatments, then and two replicates, T equal to 3 and R equal to 2. We are going to use 2 replicate and 3 treatments. Then altogether we need 6 experimental units. Then we have to divide our experimental area into 6, or experimental material into 6 groups. Now we have 6 plots, say, and now we need to apply these treatment to these 6 plots randomly. So we can use random number table, or we can write 6 sheets where in 2 sheets we write T1, another 2 sheets we write T2, another 2 sheet we write T3, and put into a container, mix it well, and take one number. So assume we got T2, then for first plot, we have to apply T2. T2. Likewise, according to order you are getting treatment, you have to apply to this plot of land. Then assume here also we applied T2. Here T1, T1, T3, T3. So all the three treatments we assign at same time to all the plots. We use only one randomization scheme. You will understand difference when we discuss the RCBD. Here, all the plots, all the 6 plots, we assign treatment by one randomization. In this design, we can use any number of treatments. Here we have used 3 treatments. We can use 5, 6, 7, any number of treatments and any number of replicates. Here we have used 2. We can use 7, 8, 10, any number of replicates. But some other design, this is not possible. According to design, we have to limit the number of treatment and number of replicates. Here it is not limited. We have flexibility. As I explained, here first what you have to do is decide the number of treatment and number of replicate to be used in the experiment. Then select required number of homogeneous experimental unit or subjects. Earlier, we needed 6 experimental units to apply 2 treatment with 3 treatment with 2 replicates. So we selected 6 experimental units. Then next what you have to do is number each experimental unit starting from 1. Here first you can number these experimental units. This is first experimental unit, this is second experimental unit, third experimental unit, fourth, fifth and sixth number. Then select T into R random numbers starting from random point of random number table. You know how to draw the random numbers from random number table. Here you have to choose 6 random numbers from the random number table since we have 6 experimental unit. Then rank those random number. You have to rank selected random numbers, selected 6 random numbers. Then group those random number into 3 number of groups. Here we have 3 treatments, 3. So you have to group these selected random number into 3 groups. And in each group you will have R random number. So when you divide that 6, when you divide your numbers 1, 2, 3, 4, 5, 6 into T number of groups, T is 3. Here, this is one group. This is another group. This is another group. So, this is first group. This is second group. This is third group. So, we have 3 treatments. So, we divided our random numbers into 3 groups. So, each contain R number of random numbers. Here, R is 2, 1 and 2. Here also 2, 1 and 2, 1 and 2. So, now you can assign treatments. First treatment, second treatment, and third treatment to random numbers which receive particular rank here. I didn't draw random numbers and I don't know what are the rank received for those random numbers. Accordingly, you can apply your treatments to plots which received rank of this random number. Assume this is received a rank of 3. So to plot number 3, you apply treatment number 1. This random number received rank number 5. Then plot number 5 also you have to apply treatment 1 likewise. Here, something very important you should understand is how these observations are made. We call that as the linear model. Here, you know, this is the first observation which has applied first treatment. This is the second observation which has applied second treatment. Third observation which has applied first treatment. So, to this plot or animal, we have applied first treatment. This is an observation, therefore, I denote it using Y and I have applied first treatment here. So, first treatment, first subscript correspond to treatment. And I have applied, this is the fourth replicate of first treatment. So, this observation I can denote using Y14. It is belong to first treatment and fourth replicate. So, here observed value is 13. 13. So, 13 is Y14. This observation has made from 3 components. What are those 3 components? Are mu. Mu represent the total population mean. Total population mean. Assume this is a goat population. So for the goat, there is an average weight. Assume it is 25 kilograms. For cows, there is average weight. Assume it is 300 kilograms. So weight of cow population different from weight of goat population. So we have a weight for population weight for cows as well as population weight for goat. So this mu represent that population mean. So this third observed value 13 has made up of some component from the population goat population. This cannot be 300 something because it is a goat. There is a possibility to possible weight for goat. It is decided by this population mean. And then there is a contribution from this treatment T1. So this tau y we call as tau y represent the contribution given by this treatment to this observation. That is 13. There is a contribution from this treatment also. Even though we have applied same treatment to this co-experimental unit, their weights are different. That is due to error or residual. So there is a contribution from residual also to this 13. So other part contributing to this observed value 13 is residual. So you can see this 13 has made up of 3 components. First component is population component. Other one is from the treatment component and other one is from the residual component, error component. So in this, all these observation, 19 or 22 or any other observation has made up of 3 things. First one is grand mean of the population. Second one is effect of ith treatment. So treatment applied for that experimental unit and experimental error corresponding to each of these observation. Experimental error in ith replicate, jth replicate of ith treatment. So in analysis, I told we use ANOVA, analysis of variance. Therefore, first we need to find out the total observed variation of this data set, total observed variation. We know the formula to calculate the total observed variation. Here, what you have to do, first you have to square each and every observation. Here, Yij represent jth replicate of ith treatment. So this observation is Y11, 16 is Y11 because we have applied treatment and it is the first replicate of first treatment. So this is treatment number also 1, replicate number also 1. So this observation is Y11. This is Y12. So Ij represent any of these values, any of these values. Therefore, this meaning you have to first square each of these values, then get the summation. So you have to square 16, 19, 24, 21, 20, 21, 18, 21, 22, 13, 20, 25. Square all these observations and take the summation of those squared observations. Then you will get this one. Then this meaning y dot dot square. Y dot dot represent the grand total of the observation. That means in order to find y dot dot, what you have to do, you have to add these observation together. 16 plus 21 plus 18 plus 13 plus 19 plus 20 plus 21 plus add all these things. Then you will get the y dot dot. Then square that total and divide by number of observation, that is T into R. In that way, you can get the total variability in this data set. That is that much. Then from that, you can identify the treatment variability, treatment sums of square. In order to get the treatment sums of square, what you have to do, you have to take the each treatment total. Here, yi dot. I represent the treatment, dot represent the total. So, first, this value will be y1 dot. That is this treatment total. That is 68. Then y2 dot, that is second treatment total, that is 80. Then third treatment total y3 dot, that is 92. So you have to square all these things. Now you have found y1 dot, y2 dot, y3 dot. Now square these things. Now divide this squared total of treatment by number of replicate that we are adding. Here, in order to get this 68, we are adding 4 observation. That is R. Here, divided this by 4. This also by 4. This also by 4. Then you have to get the summation of those things. So add this, then you will get this part. From that, deduct the correction factor, this one. Same thing. then you will get the treatment sums of square. So you have divided by total sums of square here using this formula. Now you have the treatment sums of square. So now you can identify, assume here total was 118, treatment sums of square 72, now this is 30, so 46. Now in this data set you have calculated total sums of square, treatment sums of square. Now your next step is to calculate, construct the ANOVA table. In the ANOVA table, you have different columns and different rows. So, purpose of ANOVA table is to partition this total observed variability. This total observed variability into different components, which is represented by the then linear model of the design. Linear model of the design. You can see in this observation, these are the observation Yij, there is a variability in the observation. So we have total variability here. And this has made up of population mean, treatment effect, and residual effect. So population mean is not vary here because all are gods, all are belong to same population. So there is no variability coming from this source, population mean, to here. But here there is a difference in the treatment. So for the total variability, there is a contribution from the treatment part. So it here we have a contribution for the variability. So in the residual also, there is a contribution for the variability. Even though we have applied same treatment, observation are different. There is a contribution for the variability. So for total this variability, contribution is come from treatment and residual only, not from the population value, because there is no variability in the population value. Even though this contributed to made the value, decide the value, it has 16. For this variability, this mu is not affecting. So in the ANOVA table, we have total variability. First column represent the ANOVA table. In the ANOVA table, source of variation. So in our CRD design, total variability is made up of treatment variability and residual variability. So source of variability represent the sources of variability. For the total variability, it is contributing treatment as well as residual. Then in the ANOVA table, second column is degrees of freedom column. Here, each sources of variability will have degrees of freedom. Total degree of freedom mean total number of observation minus 1. We know total number of observation we can find using T into R. T number of treatment, there we had 3 treatments and 4 replicates. Therefore, total number of observation we had 12 in our example, and minus 1 equal to total degree of freedom. How this 12 made up of? Here we had 3 treatments and 4 replicates. So 3 into 4 is 12 minus 1. This minus 1. This is the total degree of freedom. Then treatment degree of freedom calculated as number of treatment minus 1. We had 3 treatments minus 1 is the treatment degree of freedom. That is 2. And error degree of freedom we find as total degree of freedom, that is 11 here, minus all other degree of freedom, all other degree of freedom. But here we have only, except residual, we have here treatment degree of freedom only. So all other represent only treatment. So residual degree of freedom is 9. Now, third column in the ANOVA table represents the sums of square. I have given formulas to calculate each sums of square. We can calculate total sums of square by squaring each observation and getting summation of those squared observation and deducting correction factor. So it has given here this formula. We found that value for this data set as 180. This total sums of square 180. Then treatment sums of square. This is the formula. That is, you have to first get the each treatment total. First treatment total, second treatment total, third treatment total. Likewise, then square each total and divide each total by respect to number of replicates for that treatment and take summation of that product. Then from that deduct the correction factor. We can found that for our data set here, for this data set, it was 72. It was 72. Now we know total sums of square. We know treatment sums of square. Now we need to calculate the residual sums of square. Residual sums of square or error sums of square. That is equal to total sums of square minus treatment sums of square. That is this part minus this part. It is equal to 46. Then in the next column of the ANOVA table, we have mean sums of square. So mean sums of square mean this sums of square of each component. Sums of square of each component need to divide by their degree of freedom. So here treatment sums of square is treatment is 72. And in order to find the mean sums of square treatment, what we have to do, we have to divide this sums of square treatment, that is 72, by corresponding degree of freedom, that is 2. So you will get 36 there. And here, in order to find the error mean sums of square, you have to divide error sums of square error or sums of square residual, that is 46 by its degree of freedom, that is 9. So you will get I guess 5.11. 36 divided by, sorry, 46 divided by 9, 11. Here you will get 5.11. Now, in order to find the calculated value, you have to divide mean sums of square treatment. Mean sums of square treatment, we found it is 36. By, you have to divide this by mean sums of square residual. We found it as 5.11. So this will equal to calculated value. 36 divided by 5.11. That is equal to 7.04. 7.04. Now you have calculated F value. Now you need to compare this value with the F table value. From the F table, you know we have columns and rows in F table. So in this column, you find the degree of freedom related to numerator. Here in numerator we have treatment mean sums of square. Treatment. Numerator we have treatment mean sums of square. So degree of freedom related to treatment is 2. So in the column you find the 2 there, degree of freedom. And in the row you have to find the degree of freedom of denominator. In the denominator, we have mean sums of square residual, that is 5.11. Their degree of freedom is, residual degree of freedom is here, 9. So from the row, you find the 9. So this value of the F table is the F table value. If this F table value less than this calculated F value, or if this calculated F value greater than this F table value, so F cal greater than F table, we reject our null hypothesis. If F cal greater than F table, we reject null hypothesis. Rejection rule, if F cal greater than F table, reject null hypothesis. We will see another example here for our CRD design. An experiment was conducted to evaluate 3 treatments. Those treatment has given as T1, T2, T3, each with 2 replicates. In the CRD design is CRD, we have 2 replicates for each treatment and there are 3 treatments. The experimental layout and observation of each experimental unit are given below. Conduct appropriate analysis to test whether there is a treatment effect. So we have designed our experiment and conducted our experiment according to CRD design. And at the end of the experimental period, we have measured or obtained the reading from this design. These are the readings. We have applied 3 treatments according to CRD design and 2 replicates. So first replicate which applied first treatment gave 2 units. Second replicate has given 3 units at the end of the experiment period. Similarly, first replicate which applied second treatment has given 5 units and second replicate has given 6 units. And observation which applied third treatment has given 2 unit and second replicate has given 1 unit. So these are the observed data. You can see there is a variability in this observation. So first we have to calculate total variability of this observation, then calculate the treatment variability, then from total variability deduct the treatment variability and identify the residual variability, then construct the ANOVA table and uh, then do the F test and give conclusion. So we will do it first calculation of sums of square, total sums of square. You know this is the formula. Here what you have to do is you have to square each and every observation and get the total. So these are your observation 2, 5, 2, 1, 3 and 6. Now square each and every observation. This is the squared observation. Then the get total of this squared observation, that is equal to 79. And next you need to find the correction factor. In order to find the correction factor, what you have to do, first you have to find the y dot dot, y dot dot, y dot dot, y dot dot mean total of all the observation, total of all the observation, that is total of these observation, that is 19. So now square that value 19 and divide by number of observation, that is t into r. T is 3, r is 2, so 6. Now you will get here, this one is 79 and this is 19 square divided by 6. Then when you deduct this value from this, you will get 18.8. Now you have found the total sums of square of these observations. Next, you need to find the treatment sums of square. In order to find the treatment sums of square, you know the formula. Here, first you need to find the y I dot. Here I dot, since we have 3 treatments, first it will be y1 dot, second y2 dot, third y3 dot. We have only 3 treatments. So y1 dot mean first treatment total. First treatment total, you see we have applied first treatment to 2 experimental unit, that is to this experimental unit and this experimental unit. So total of first treatment will be 5. 2 plus 3, 5. 5. Likewise, find the second treatment total, that is 11, and third treatment total, that is 3. So now you have find each total of each treatment. Now you have to square those totals. Now you have to square 5, 11 and 3. Square each total. Then divide by number of replicate we added to get this total. We added 2 observation to get this total. We added 2 observation to get this total. Here also we added 2 observation to get total. So divide by 2. Now get the summation of this thing. Get the summation. So you will get this part, and from that you have to deduct this, that is correction factor, that is total of the observation square divided by number of observations. So you will get that as 17.33. This value is 17.33. Now, next step is to construct the ANOVA table. Before that, you need to write the hypothesis. Hypothesis, you know, in statistical test, there are two hypotheses we have to write. First hypothesis we called as null hypothesis. Second hypothesis we called as alternative hypothesis. In the null hypothesis, we assume all the treatment means are same. All the treatment means are same. That can be written in symbolically using mu1 equal to mu2 equal to mu3. That is mean of treatment population 1 equal to mean of treatment population 2 equal to mean of treatment population 3. All population means are equal. And if all the population are not equal, the possibility is at least two treatment populations are different. At least two are different. Symbolically, we can write this as mu I not equal to mu j. I may be 1, j may be 2. So, 1 not equal to 2. First treatment may not equal to 2. Or first treatment may not equal to 3. Or second treatment may not equal to 3. Any one of this combination we can write using this symbol. Mu I not equal to mu j. For some I and j. I may be any value or j may be any value. So this may be 1, this may be 2, this may be 1, this may be 3, this may be 2, this may be 3. Where I not equal j. So this cannot be 1 and 1. So that is the meaning of that. So before constructing the ANOVA table, you have to write this null hypothesis and alternative hypothesis. In simple, you can write null hypothesis as all treatment means are same. Here is not that in exam or in your questions, you have to write not all treatment means are equal. Here we have applied assume varieties, then you have to write as all varietal means are equal. All mean of all varieties are equal. Mean of all diet are equal. Likewise, in the alternative hypothesis, you have to write at least mean of two diets are different. At least mean of two diets are different. At least mean of two varieties are different. At least milk yield of two cow varieties breeds are different. Likewise. Then construction of ANOVA table. You know, in the ANOVA table, we have 6 columns. First one represent the source of variation. Second one, degrees of freedom. Third one, sums of square. Fourth one, mean sums of square. The fifth one, F calculated value. Next one, F table value. Here, under the source of variation, since this is CRD design, total variability break into two, that is treatment variability and residual variability. So, under the degrees of freedom, in this example, we had 6 number of observation, that is 3 treatments and 2 replicate, 6. The 6 number of observation. From that, we have to deduct 1 in order to find the total degrees of freedom, that is 5. Then here we had 3 treatments, so T equal to 3 minus 1 equal to 2. So the treatment degree of freedom is equal to 2. So residual can be found by deducting all other degree of freedom from the total degree of freedom. So total degree of freedom is 5. Sum of all other degree of freedom is 2 because we have only treatment source. So 5 minus 2 is 3. Now next column is sums of squares. We have found these sums of square earlier using formulas. Here total sums of square was 18.83 and treatment sums of square was 17.33. So in order to find the residual sums of square, you have to deduct treatment sums of square from the total sums of square. So residual sums of square will be 1.5. Next, what you have to find is mean sums of square. So mean sums of square can be calculated by dividing corresponding sums of square by the degree of freedom. So in order to find the treatment mean sums of square, what you have to do, you have to divide treatment sums of square by treatment degree of freedom. So you have to divide the 17.33 by 2. You will get 8.66. Then in order to find the residual mean sums of square, you have to divide the residual sums of square by residual degree of freedom. So 1.5 need to divide by 3 equal to 0.5. So in order to find the calculated value, you have to divide mean sums of square treatment by mean sums of square residual. So mean sums of square treatment is 8.665 and mean sums of square residual is 0.5. So this divided by this will result 17.33. And now you need to find the F table value. F table value, when you finding F table value, refer to the table of alpha equal to 0.05 in there. In the, as you know, in the column you have to find the degree of freedom related to treatment. Degree of freedom related to treatment. In the row you have to find the degree of freedom related to residual. Here degree of freedom treatment is 2, residual is 3. You can find the corresponding value from the table. It will be 9.6. So you can see if cal value greater than a table value. That means this difference in the sums occurred in the population also. So we called as these are significantly different. These are significantly different. Therefore, there is a significant treatment difference. So decision if cal greater than F table. So reject the H naught. When the F cal value greater than F table value, we can reject the null hypothesis. The null hypothesis what we call all treatment means are same. All treatment means are same. Now this is rejected because F cal greater than F table. When this is rejecting, this is automatically accepting. That means at least 2 treatment means are different. So in this example, at least 2 treatment means are different. Conclusion, at least 1 treatment is different from other. එකක් හරි අනිත් ඒවාගේ වෙනස්. At least 1 treatment is different from other. In order to find which is the different treatment, we have another technique will be discussed later. That is called mean separation technique. Then advantage of CRD, this design is completely flexible for number of treatment and number of replicate. We can use any number of treatment and any number of replicate with this design. Second advantage is missing observation are no problem. So sometime when you conducting your experiment as design, sometime while you are going experiment, some animal may get die. Some plot may damaged by animal. So you cannot get this reading. So this will be missing. So in the CRD design, even there are few missing observation, it will not be problem. You can analyze the data. For some other design, it will be a problem. Other thing is maximum error degree of freedom of any design. Here in the ANOVA table, you can see we have error degree of freedom here. In the CRD design, we have maximum error degree of freedom from any design to CRD. So when error degree of freedom is higher, it is advantage. When there is a treatment effect, we can detect. So higher error degree of freedom is with the CRD design. It is an advantage. Disadvantages: required uniform experimental unit. We need experimental area and experimental materials, or experimental unit be homogeneous. Sometimes there will be practical problem in finding homogeneous experimental material and homogeneous land area. So it is a problem in CRD. Another is all non-treatment variation is considered as error. So in this experiment, sometime in addition to treatment effect, there might be moisture variation in the land. So if we applied same treatment here and we encountered this as residual, but here moisture effect also. Using CRD design, we cannot remove that. So that is a disadvantage. We have some other design which can remove this other effect.